Assalamualaikum good morning. Continue. Speak. Speak is about the erosion, sanitation, equity, go in detail the model for water erosion, few calculation. So this is based on soil conservation and management. Slide is very good. Okay, slide is very good. This is based on chapter 3. So modeling erosion. Modeling erosion is important to understand the process governing soil erosion, predicting the runoff and the soil erosion rate. In last week, we calculate a bit about the soil erosion rate, but there's a few models which can be used to estimate the soil erosion rate. Identifying or choosing appropriate measure of erosion control, yes. We will have chapter 13 later on. How to some sort of designing the mechanical structure to minimize the soil erosion. So modeling soil erosion allow for the understanding of the driving process of erosion. The second one is based on book page 53, relation of on-site and off-site impact of erosion on soil productivity, water and pollution. So by doing the model, you can get at least 5 information. The third one is the identification of strategies for erosion control. Later we see there's a many type of mechanical structure that can be used to prevent, but which one is the most suitable? Fourth, assessment of the performance of soil conservation practice for reducing water and wind erosion, and fifth, the assessment and comparison of the soil erosion model. As I said, there's a few model to be used. Pen on that. However, there's a limitation for the model as well as its benefit. So no model can completely replicate field observation. Model can, however, provide valuable information on soil erosion trend and relative differences in erosion rate among different practices while allowing exploration and understanding of the driving force of the soil erosion. Empirical model. So many empirical models have been developed since 1900. So the first one is 3.1 equal to C prime L 0.6 and 0.4. So the keyword here is the empirical model. The word empirical refer to the it's a way of representing a system based on the observation and the data rather than nomenclature. We call it the first principle. So how they come up with the model? They do some experiment. So from the experiment, they relate it. Maybe they see if you change this variable but manipulate this variable, it will affect another variable. So they create the empirical model based on the observation. So, so where A is the average annual soil loss, C prime is the coefficient, L is slope length. So coefficient is because there are not sure how using do it in 1940, but normally when you change this variable, then another variable will be changed as well. So to make it equal, you need the coefficient. So that is that coefficient C prime. L is the slope length, S is the slope gradient. In 1941, still in the book, page 54, in 1941, from the 3.1, the first equation, there's another equation coming from Smith. So what he do, he add P, observation practice factor P. And in this case, because the first coefficient C prime is uh, unique unique to the 3.1, so we use another expression C double prime. Others is the same. L.6, S.4. So there's a few equation in the book starting from 3.1 and until the one that we will discuss in detail after this, which is the USLE, Universal Soil Loss Equation. This is published in 1965, but the starting equation is from 3.1. So it's developed until 1965. Even the equation USLE 1965, there's a improvement from it. We have a modified USLE or MUSLE. We have a revised USLE or RUSLE 1 and 2. So it's evolving. So the average annual soil loss is on SNE 1965 is equal to R times K times LS times C times P. A is the average soil loss, megagram ton per hectare. R is rainfall and runoff erosivity index EI for the location of interest. Later we discuss each of the one. Later here, the variable. Then K erodibility factor, L is the topographic factor, C is cover and management factor, P is the support practice factor. So the early version of USLE were exclusively solved using table and figure. The continued improvement has resulted in the modified and the revised USLE. So what does this equation do? It's specifically predict a long-term annual average estimate of soil loss from small plot or field segment with defined dimension. It has sometimes been used inappropriately applied to soil and land use conditions that are different from those for which the equation was developed. So there's a limitation to USLE 1965. That's why there are some modification, revision to the original 1965 equation. So USLE, unlike process-based model, the USLE cannot simulate the following. The runoff nutrient and soil loss from watershed of field scale area, soil loss on an event or daily basis, probability of soil loss from storm to storm, interreal, real valley and stream bank erosion separately, process of concentrated flow, flow channelization, and sediment deposition, and the detailed process like the detachment, transport, and the deposition. So R, the first letter in the USLE section, the rainfall and runoff erosivity index. The EI, which is the same as R in equation 3.1, is computed as the product of total storm energy times the maximum 30-minute intensity of the rain. So EI equal to E multiply I, where E is the D at equation 3.7. So D is the rainfall depth, I is the 30-minute rain intensity. So USLE uses the annual EI, which is computed by adding the EI value from the individual storm that occurred during the year. So some limitation for the USLE computed EI here. Question 3.6, 3.7. It is only valid for rain intensity less than 63.5 meter per hour. So this is the map of runoff erosibility index or R. Data on R for different locations on the continental USA and estimate for the world are available in the US, about 4,000 sites analyzed. For the rainfall intensity for a range of written period to develop an ISO erosion map is 3.1 to 3.1. Value of EI30 below 500 correspond to dry region, and thus 500 above is correspond to the humid region. So this is R. So let's say, for example, so compute the I for a rainstorm of 30 millimeter in 1 hour. Okay, so storm duration is an hour. Storm depth is 3 cm. Storm intensity is 3 cm per hour. Plugin value D. So D is depth. I is the storm intensity. Then another I. So inside the equation, we got I is to I to 2.72 EI. So the rainfall and runoff velocity index R, this case is 22.72 because the I is equal to R. So for this, how to use this map? So let's say the location that is limited to US, the is available there. For example, if the point that you want to check to identify the R index for here, in between how much? So, here, in between 4,000 and 5,000, so you can estimate how much R is here. So for 4,000, this is a limit region. They have a soil erodibility factor. So soil erodibility factor refer to the soil susceptibility to erosion. So the K value for the development of USLE were obtained by direct measurement of soil erosion from fallow and raw crop plots across a number of sites in the USA, primarily under simulated rainfall. The K value are now typically obtained from a monograph. So monograph refer to the similar to figure 3.1 value of R. So the K value are typically obtained from the following equation. So there are two ways to identify value of K. You can obtain it from monograph. Similar study, but not the figure 3.1. That one is for R. But from the same study by the Foster et al. 1981, there's a value of K similar to style that we found in figure 3.1. The map of US with the contour and value of K. Or you can use this equation 3.8 and 3.9. So each of letter here, A, B, C, and ABC is based on the profile. So where M is the particle matter, A is the percent of soil organic matter content, B is soil structure code. So if the soil is a very fine granular, so B is equal to 1. If the soil is blocky, flaky, or massive, so B equal to 4. Depend on the description of the soil in the question. The NC profile permeability, saturated hydraulic conductivity, this is also either you calculate or given in the question. So for C equal to 1, it must be rapid, which is 150 millimeter per hour. More than 150 millimeter per hour. C equal to 4 is slow to moderate. The last one is 6, very slow, less than 1 mm. The size of soil fraction, so soil particle for very fine and fraction range between 0.5 and 0.05 and 0.1 mm. So the soil organic matter content, the soil organic matter content is computed as the product of percent organic C and 1.72. So C, total organic carbon, multiply with 1.72. That is how you get the value for A. Or it's given in the question. Topographic factor LS. So USLE compute the LS factor as a ratio of soil loss from a soil of interest to that from a standard USLE plot of 22.1 meter in length with 9% slope as follow. So this is referred to equation 3.1 to 312. So where S is the field slope percentage and theta is the field slope steepness in degree. So the steepness, how does it calculate? So it's based on the length of y and x. Yes. So when it's downhill, down slope, so x is negative. Later there will be a example. Cover management factor, this depends on table 3.1. So the C factor is based on the concept that soil loss, changes in response to the vegetative cover, crop cover during the first stage period, rough fellow seedling establishment, growing, maturing crop, and residue or stubble. Computed as the soil loss ratio on a field under a given crop stage. The C factor vary with subfactors such as canopy cover, amount of residual life on the surface. Combine, okay. This is the table 3.1. So you need to remember USLE question. There's a few index, R, K, N, S, and this is C. So how to use it is depend on the description of the land of the soil. So let's say the soil is for corn plantation. So for the continuous corn, the description based on that, moldboard plow, residue plow during fall, spring chisel plow, more than 50% residue cover. So the value of C based on the description inside the patient, or when you describe it, the actual plant area. You need to choose value for C. Next is P. How many? Okay, P is the last one. Support practice factor. So the P factor refers to the practice that are used to control erosion, defined as the ratio of soil loss from a field with support practice to soil loss from a field on the up and down slope tillage. Without these practices, the p-value vary from 0 to 1, where the highest value corresponds to the field without any support practices. So the support practices including contouring, contour strip cropping, terracing, grass watering. So the support practice here is we can say it's a mechanical structure to control the erosion. In system with various support practice, p-value are plotted as follow. So 3.13, where PC is the contouring factor for a given field slope. PS is the strip cropping factor, and PT is a terrace sedimentation factor. So this is in table 3.2, 3.3. So you need to identify the PC, PS, and PT put together. It's a value for P, support practice factor. So you see, this is the contouring, which is the PC, strip cropping, PS. Then we have a terrace factor, PT. Example 2. So 130-meter long fin with a 5% slope is under continuous coordination with a chisel plowing in eastern Nebraska. The soil is sit low, 10% coarse, and 20%, 10% very fine sand, 80% clay, and 60% silt. With 2.5% of soil organic matter content, the structure is medium or post-granular, and the saturated hydraulic conductivity is 50 millimeter per hour. Estimate the average annual soil loss if the field is contact and strip crop with no damage. So the example asking you to calculate a soil loss, soil loss. So to calculate the annual soil loss, to use SLE equation, which is equation 3.5 to R, K, N, S, C, and P. So, the rainfall erosivity, which is the first letter R, first index R, is 2,500. So how do you know? So this is the state of Nebraska. So the R, follow the line. 1,000, 1,500, which is this one. Eastern Nebraska. So kat bawah. Eastern Nebraska. So this is 2,500. R, 2,000. Next is value of K. So K, this is depend on equation 3.8. So for 3.8, there's a value for A, B, C, and M is based on the description by the question. You see the soil is sit loam, 10% coarse, 10% very fine, 20% clay, 60% silt. So sit, how many percent? 60. Very fine sand is 10 times 100 minus clay. Clay is 20%. So M equal to 5,600. How about A? So A here is 2.5. As on the description, A is the soil organic matter content, which is given in the question, with 2.5% of soil organic matter content. So A equal to 2.5. B is okay, there's a description for B. It's a soil structure. So in this case, this is the structure is medium of coarse granular. Medium of coarse granular. So B is equal to 3. This is based on description given in page 57. C is based on the, let's see, the profile permeability or saturated hydraulic conductivity. So based on the question, it's a 40 mm per hour. So 40 mm per hour fall under moderate, which is the 12 to 50 mm per hour, with index C is equal to 3. C equal to 3. So in value F is 5,600, indicate K to 0.54. Next is topographic. So LS. So for topographic, S is the percentage of slope. In this case, slope is 5%. So, yeah. So 5 divided by 100 is 0.05. Then we have theta. Need to find determine S. Then we can get theta. So once you get M and theta, you just plug in into equation. Uh, 3.1. 3.1. So the length is given in the question, which is 130 meter long film. So this is 130 meter. To the power of M. So M here is 0.499. Then since square theta, this is theta or theta. Plug in, we will get LS equal to 1.106. Next is the C value, which is the cover management factor. So for value of C, you need to refer to table 3.1, page 59. So based on the description, this is a continuous cone managed with the chisel plowing. Continuous cone managed with the chisel plow. So the value of C is 0.2. Then the last one is the support practice factor. So for the support practice factor, this is a PC and PS is based on. So equation for support practice factor P, equation 3.13. So you need to identify value for PC, PS, and PT. So for value PC, this is slope with 5%. So value of P is 0.5. Then we have 5% again. Then 0.25. Okay. And for PT, oh, there's no terrace. Terrace is it. So with the terrace, P is not equal to 0, it's equal to 1. 1 equal to 0. This P equal to 0. So PC is 0.5, PS is 0.25, PT is 1. Because no terrace. Then once you determine all the index, factor or value for the unknown, the variable, then we can calculate the value of A. So in this case, A is equal to, in this case, A is equal to 3.73. Another equation, estimate the soil loss if the crop field had been managed without contouring and strip cropping. So under this new condition, p value would be equal to 1. Does A equal to? Okay. Estimate the soil if the crop field had been managed without contouring and strip cropping. So meaning, tak ada terrace, tak ada contouring, tak ada strip cropping. So all PC, PT, PS is equal to 1. That's why P is equal to 1. So the soil loss is a lot, like a lot. With the support factor, you might lose 3 ton per year, per hectare, sorry. This is per year as well, because this is a annual soil loss. Then if without the support factor, the loss is 29 ton per hectare per year. One is a lot. So this is the model. So from the modeling, we can see, okay, this area can do the calculation and estimate how much the soil will be lost in a year. So if we put a support to this area, like a contouring, terracing, so we can reduce this soil loss up to this level. That is why we do the modeling. Modify USLE. The MUSLE is a modified form of USLE, while USLE predicts sediment yield or soil loss based on rainfall. Mostly predict it by using the runoff factor, which account for the antecedent soil water content. Okay. This modification allow the use of USLE for predicting sediment noise on a storm event basis. So sediment So SED, the sediment yield on storm event basis. This is equation 314. Okay. And 315. So CFRG is cost fragment factor. A is the area of hydrologic response unit HRU. Okay. There's no example how to use modified ESLE. This is for information. Revised USLE. This model is more comprehensive and detailed than the US model. It is based on empirical and process-based approach. The RUSLE is the most commonly used water erosion model globally worldwide. USLE. So as compared to USLE, it includes more EI value for different regions in the US. It can incorporate soil processes like freezing and thawing and changes in water content into the USLE. So to compute revised USLE, you need a computer tool to calculate the LS interaction based on the field and interim erosion relationship. So the equation, there are two forms of RUSLE. So both RUSLE 1 and 2 can compute the TC, which is the transport capacity. So KT here is transport capacity depend on the hydraulic resistance of soil surface roughness and vegetative cover. And QP is the runoff rate. No? Then sediment deposition T is estimated as equation 3.17. Okay. This is the process-based model. So what we have learned is the empirical model. So the process-based model, the fundamental principle for all complex model and simplifying equation of transport of sediment transport prediction is the continuity equation of mass, which is delta QS. This is a 318. So delta, you see the delta here, meaning the process is a dynamic. It changes over in this case, over the distance of the downslope. For CY, C is the sediment concentration, Y is the flow depth, and T is time. So for some changes or specific changes of time, the C and Y is changed as well. That's why they use the time. So this is the process-based model. So how to use this? Normally we do simple integration to account for the changes in two variables. So the first term dqs over dx represent the change of sediment flow rate with respect to distant x, whereas the rho s delta cy over delta t represent the change in sediment storage with respect to time. If the sediment flow is shallow, The storage term may be negligible and we have, okay, so if the sediment flow is shallow, so we can ignore the middle expression here. So equation 318 simplified to equation 319. Exercise. Exercise. Estimate the average annual soil loss for 300-meter field. Chisel plow in spring under corn soybean rotation in eastern Nebraska. The soil is sheet loam, 17 cost, 2%, 3% very fine sand, 32% clay. All right. So this is USLE soil loss. The equation 3.1. 3.5. 10 minutes is enough. We do this first. Any question you can ask. And don't forget to submit the report project. So to answer this question, first you need to identify the question first. So the question is 3.5. SLE average and one loss. So you do it factor by factor. Try search for R first. So this is Eastern Nebraska. So R is equal to 2,500. Then calculate for K. So K here is a bit tricky. You need to identify, normally start with M, so percent of sale is 58 plus very fine sand is 3. 5 plus 3 times 100 minus clay is 52. How about A? A is the soil organic matter content, which is 3.1. Then B is structure is fine granular, and fine granular means B equal to 2 because 1 is very fine granular. 2 is fine granular. So B is equal to 2, C is equal to, based on the 55 millimeter per hour, the hydraulic productivity. 55 is between moderate to rapid, 50 to 150 millimeter per hour. So C equal to 2. Next is the topographic factor LS. So for the LS, you need to identify the S. S here is a S. 3.8%. So find M, question 3.11. So S here is 3.8% divided by 100. Then calculate for the slope theta, which is tangent minus tangent -1, S over 100. Then plug in the value to 3.1, you get the LS. For the cover management factor, index C. So index C, you need to refer to table 3.1 for some value of C. So since this is a corn soybean rotation, so corn soybean rotation, the fourth row, corn soybean rotation, right? Chisel plow. So chisel plow, C is equal to 0.23. Next is CP, okay, support practice factor. So the sum erosion control practice is used, P factor is 0.5. So no need to refer to a table 3.2, 3.3, just use P equal to 0.5. So you get the all the index ready, plug in into equation 3.5, determine the annual soil loss. Oops. Mechanical structure and engineering technique. This is based on chapter 13, page 299. Type of structure. So mechanical or engineering structure are designed to manage runoff and soil erosion in field where biological control practices alone are insufficient to reduce soil erosion to permissible level. A number of mechanical and engineering structures are available, some of which are permanent and others temporary. Temporary measures include counterbands, sandbags, planks, structure mats, lock barrier, while the permanent structure include terrace, drop structure, spillway, culvert, and many more. Hanjak. So mechanical structure are designed to actually the list is quite long, meaning it's important. Yeah. So some of it is to intercept and reduce the runoff velocity, pond and store runoff water, and convey runoff at non-erosive velocity below. So counterbanding consists of establishing earth or stone embankment 1 to 2 meter width on the field contour to reduce the runoff velocity. So counterbanding consists of establishing earth or stone embankment of 1 to 2 meter width on the field contour to reduce the runoff velocity. This band divides the field into nearly parallel segments for reducing the effective slope length. The counterband appropriate for field with permeable soil of gentle to moderate slope, less than 10%. So this is the example of the bar. This is the stone bar. So stone bar laid out perpendicularly to the dominant slope are popular in mountainous region for reducing soil loss from the integrated effect of water, wind, and tillage erosion. A well-maintained stone bund developed terrace and decrease the slope length. So some example in the book, page 300. In the highland of Ethiopia, mean soil loss of 20 ton per hectare from cultivated land decreased to a negligible amount with the introduction of stone bund. There's another one in Mali. The same thing happened. Okay. Many more examples in the book. But all of the example indicate that if we put some support factor uh, to the slope, it will reduce the amount of minimal soil loss. Then silk fence. Silk fence a barrier consisting of woven consisting of woven and non-woven unwoven geotextile fabric product anchored to vertical metal or wooden posts which are arranged on the contour across the slope for reducing runoff velocity and filtering sediments. It's like this. This is the silk fence. But silk fence is considered as a temporary measure. Unlike the permanent structure like this contour band. So, okay, silk fence are installed at parallel interval or hill slope. But this is the problem with the temporary measure. It might fail. This is how the sediment accumulation above siphon can overtop the fence under concentrated flow erosion. But why we choose fencing? Because of it, uh, relatively low cost and the simplicity of it. The use of seed fence is preferred by construction industry, mining companies, and soil conservation program for reducing off-site soil transport from disturbed site. Okay. So some calculation, the flow rate through the seed fence can be estimated by equation 13.1 or 13.2, where C is the coefficient of discharge. A is, so when you see this word coefficient, meaning it's a most likely is a empirical model. A is area of the orifice. is the acceleration due to gravity, h is depth of conduct water upslope of the fan, m is the number of openings, dt is the opening size in the horizontal direction. So there's a expression here. This one. This symbol is equal to question 13 point infinite fluid. What is I? Without n is the total number of occurring in the vertical direction. So I equal to 1. Yeah, I equal to 1. So how many number of the opening? So that is n. Compound. The compound is in page 304. Agriculture use more than 70% of the world freshwater for irrigation, which is true. However, availability of freshwater is warming due to intensive agriculture, increase in urbanization, the cell uses and use of water resources. The farm pond are structure designed to harvest water while controlling water erosion and flood. There are four types of pond: groundwater fed pond, stream spring fed pond, upstream pond fed with diverted water, and rain fed pond. So the groundwater fed pond. So this pond we also call the dugout pond, rely on shallow water table and are constructed in low-lying areas with slope less than 5%, where the prevailing water table is near the soil surface about 1 meter. These ponds are relatively inexpensive to build. The collecting groundwater in pond may be mentioned to lower the water table in poorly drained soil. Okay, and then we have a stream and spring fed pond. So the stream pond are established across the stream or below a spring to capture a fraction of the continuous or intermittent flow of water. So for this purpose, dams are constructed in depression across stream without completely blocking the passing water. Then we have upstream pond and rain-fed pond. So rain-fed pond, the most common type of pond in water limited region. The source of water or rain-fed pond is a surface runoff. This pond are installed later. There's a design, how to design pond. How big is the pond needed to get a certain amount of so usage or stop kettle stop. Design and installation of pond. Proper design of pond is important to reduce the runoff, store water, reduce water losses to seepage and overflow, and allow water availability to grow. Suitable site should be selected based on rainfall pattern, soil hydrology, land use, and topographic features. So factors which influence pond design include mm, watershed, size, soil textural characteristic, soil hydrology, slope gradient, tillage and cropping system, rainfall pattern, runoff amount, and the seepage problem. So water seepage. So, water seepage is a major source of water loss from a pond. So the compaction, water seepage means it's seep into the soil itself. So compaction and lining with impermeable materials such as clay or plastic sheeting are the strategies to reduce seepage in small pond. The volume of runoff available for harvesting can be calculated using equation 2.19 already discussed underwater erosion, which is S equal to 25,400 CN minus 254. The pond depth is a function of evapotranspiration rate, cost of construction, safety, slope gradient, and then availability. For instance, shallower pond about 1 meter deep may lose significant amount of water through evaporation but are relatively less expensive. The depth of the pond, the drainage or watershed area, WA required per pond, a number of pond for floating about 1,000 meter cube are estimated using equation 13.4. Okay. D equal to 1 plus evaporation minus rainfall plus seepage. So D is depth of the pond. So the D is set to 1 when D is negative. The desired D can be used to adjust the WA, watershed area, WA, using question 13.5, 1, where RF is the average runoff depth available. The number of pond is computed based on question 13.6. NP refer to number of ponds, so TWA divided by WA, TWA is the total watershed area. Okay. Example, design a pond to supply water to 50 milk cow, 100 sheep, 0.5 hectares of vegetable under drip irrigation and family size of 5 in an arid region. So what is arid? It's a dry region. Assume that losses of water in the pond by evaporation and seepage about 50%. This is a lot. The average annual precipitation is 500 millimeter and the runoff curve number is 70. Runoff curve number, that one is CN value. To calculate runoff S, so we need the CN. So CN, we go back to chapter 2 or 3. Chapter 2, the erosion. There's a table to calculate to determine the value of CN. So refer to table 13.1. 13.1 ada. So 13.1 refer to page 308. That is an approximate water requirement in the USA. So the type of water used, so this is estimate. See, example is human use per person is 190 to 380 milliliter per day, which is how much water that we use. How about milk cow? It require 132. Chicken require 34 liter per day. Other than that, sprinkler irrigation per hectare and day is 6,000 something, 6,021, 6,121. Drip irrigation is 1,530 liter per day. So the annual requirement of water. So how does they come up with the WR? So WR is refer back to table 13.1. For example, cow there, see? So each cow require 132 liter per day. So 50 cow is 50 multiplied with 132, we get 6,600. It's a lot of water. 6,600 liter per day, or 2,409 meter cube per year. And calculate for all. How about 3060? So 3060 here refer to the drip irrigation, because if you refer to table 13.1, the simple sprinkler irrigation is based on hectare. So since this is a 0.5 hectare, so it's half, 6121, which is 3060. So in total, water requirement, annual water requirement is 4,338. So which must be adjusted for the annual loss. So 4,338 divided by 1 minus 0.5, because seepage by 0.5. So required water annually is at 676. The pond must have a capacity of at 676 to satisfy the annual local requirement. The amount of runoff is estimated as this is equation last week. Yeah? So S equal to 108.9 calculate Q. Is what we found. So the S here, this is on calculation to go to page 44. Hmm. So Q referred to equation 2.19. Although it's using I here, it's the same. In equation 219, it's RD. RD is the amount of rainfall for the day. So I here is it should be 500 mm. Yeah. This one 500 mm. Annual precipitation. So this one is 500 minus 0.2. Okay. All right. So Q is depth of runoff. This one. S is 2. S the retention parameter. Retention parameter. SQ drainage were already required based on the equation. So the equation, but it's a WR over Q. So how much required? 2.2 hectare. 2.2 hectare. Saya 2.2 hectare of a pond to satisfy the need of 8676 meter cube. Right. So that is calculation. Next is the terraces. So terraces are earthen embankments established across the dominant slope, partitioning the field in uniform and parallel segment for controlling soil erosion. Terraces are one of the oldest practices used to reduce soil erosion in sloping terrains. Terraces are designed to modify the original topography and are more suited to terrain with slope more than 5%. The convert sloping field into flat field, although in small parallel strip. This is terraces. So terracing decrease the LS and P value of the USLE. So LS is the topographic value. P is the support practice factor and provide the greatest benefit to soil and water conservation when used in conjunction with the proper cropping and tillage system and soil conservation structures such as grass waterway. Four main type of terraces include narrow base, broad base, steep black slope terraces, and bench terraces. There are also drainage type terraces used in region with high precipitations. High precipitation refer to having high rain, hujan, but poorly drained soil as the resorption type terraces. Or the narrow base terraces are preferred in region with limited precipitation and the soil. This is a narrow base terraces. These terraces are used in shallow and sloping land, unlike broad base terraces, and have a steep, narrow ridge, figure 13.5. Both front slope and the back slope of the narrow base terraces are planted to perennial grasses. The ridge in narrow base terraces is steeper than that in broad base terraces. Okay. So this is the broad base terraces. So broad base terraces are used in long and uniform field with slope less than 8%. And all the section of the terraces are farm, unlike narrow base terraces. They are also known as the channel terraces because the channel are all cultivated. The channel are greatly graded to outlet to runoff disposal, distress, appropriate engineering, erosion control, drainage are important. Okay. Then we have this is the broad base terraces. This is the front slope, back slope, original slope. So they dig it out and place this soil on top of here. So this is what we call front slope, back slope. This okay, this is the cut slope. Kali dari atas. And bench terraces, widely used in hilly terrain worldwide. Bench terraces are suited to field with slope more than 10%. And often have a steep back slope. The width of the bench and height of step are variable depending on the field slope. Refer to 13.7, that one. A width of 7.5 meter is used in moderately sloping land. The back width of the traces become narrower with an increase in slope gradient and length of. So design of the traces. Traces should be designed to contain runoff for rainfall event with a return period of at least 10 years and consider soil slope gradient. Risk of within terrace erosion, soil properties, field equipment with and cropping system. Traces must be properly designed to reduce interference with machinery, traffic, cropping system, and field management. They should have proper reach height and well-designed outlet channel to convey water and reduce risk of overtopping. Okay. So the cut and fill for constructing traces are determined as follows. So 13.7, stop at 13.7. For balance cross-section, figure 13.11. This figure, meaning this area is equal to this area. So C equal to F or 2C equal to 2F. So 2F equal to H plus SW or 2C equal to H plus SW. Does C equal to F equal to H plus SW divided by 2, 13.8. Where C is cut, F is fill, H is depth of channel including fall board, freeboard, S is fill slope, and W is the width of the side slope, which is equal to the unit. So terrace height is equal to channel depth plus freeboard, 13.5. What's this freeboard? Okay. So another method, this is one method, this is another method in US. Most terrace are designed based on the following relationship. Vi equal to X multiply S plus Y, where X is, okay, another one is 1310, where X is based on the geographical location. This is what we call a model graph. S is soil slope, Y is the soil condition. So Vi is the difference in height between two adjacent or succeeding terraces. Hi is the actual horizontal distance between the terraces and not the distance measured over the land surface. The number of terraces in a long field is determined by dividing the width of the field by Hi. The value of Y depends on soil erodibility and tillage and cropping system and range between 0.3 to 1.2, with commonly value, one is referred to page 3, okay, available 315. So value between 0.3 to 1.2, value 0.3 is for highly erodible soil. Okay. Value 1.2 is for soil with low erodibility and with at least 3.3 ton per hour per hectare of crop. C2 mulch. The Y value of 0.75 is for soil with moderate erodibility. For example 5. So compute the terrace spacing for a soil with moderate erodibility and 3% slope, y equal to 0.75 in Minnesota. Determine the even multiple of turn between the terrace if the width of the field equipment is 7.5 meter. So from figure 13.13, x is equal to 0.24. Why? This is the Minnesota. So this is Minnesota. So Minnesota is clearly near to x equal to 0.24. Vi is 0.24 times 3, which is the slope, plus 0.75, which is the y. Okay. So Vi is 1.47 meter. Hi, same value, different equation. The Hi must allow an even turn of field machinery. So 49 meter divided by 7.5 is 6.53. So 6.53 turn. How to calculate for 0.53? So Hi should be adjusted to 45. So divide by 7.5 meter, which is the field equipment width. So we need a 6 turn so that the field equipment could make an even turn of 6 between terraces. Next, 13.3, compute the cut and fill and front and back side slope to construct a terrace on a sloping field, 5% slope. With a balanced cross section, the terrace width is 8 meter and the channel floor depth is 0.5 meter. The freeboard is 0.15 meter. Okay. So the terrace height is equal to h equal to d plus freeboard 2.5 plus 0.15 is the terrace height 0.65 meter. The required depth of cut and fill. So C equal to F. This is equation 13.8. So 165 S is 0.05, which is a slope. W is 8 meter. Divide by 2. So C and cut and fill should have a similar value of 0.5 to 5 meter. For the front slide slope, the run overrise 8 meter divided by 0.5 to 5 is 15 to 1 or 15.24. The back slope is slope width divided by H plus S times W. So we get 9 to 1, 8.65. Gully erosion control. The erosion control one is page 318. So type of gully erosion control structure. So gully erosion control is divided into two. There are temporary and permanent structure depending on the severity of the erosion. For temporary structure is include a small dam of 3 branches, stone, constructed across the gullies. So you know gullies is one referred to last week. How does a gully look? So how to control a gully? Or temporarily you put a stone inside. For a permanent structure is to concrete to create the build a concrete channel or farm pond or concrete dam to minimize the gully erosion. We have a drop structure. This permanent structure absorbs concentrated runoff and reduce gully erosion by directing the runoff through a well-designed drop spillway. Figure 13.1. So the runoff flowing over the drop structure is into a nearly flat apron before it is carried to a stable channel. The apron stop and reduce runoff velocity. The rate of runoff passing over the structure is controlled by a box or strip inlet spillway with the depth between 0.5 and 1.5 meters. So the flow through the spillway here is calculated through way equation 13.13. So Q is the maximum discharge. This is right. C is spillway coefficient, L is spillway length, H is depth of spillway with C value. C is coefficient of spillway. C equal to 3 is used for rock. 1.8 is the gabion and section. Example 13.5. Design a pop in the drop spillway for a check dam to control gully erosion from a watershed with an area of 20 tanga. The dam will be constructed from gabion basket. The average 20-minute rainfall intensity I for a limited period of 20 years for the region is 75 millimeter per hour, where an average of 70% of rain become runoff. So using question 2.21, refer to chapter 2. First, compute the peak runoff rate Q. Okay. So A is 20 hectare or 0.2 kilometer square. Q is CI, A divided by 3.6. So C is 70%. I is the rainfall intensity, which is 75 millimeter per hour. Then A is the area of course 2.2, and Q, the peak runoff is 2.2 meter cube per second. If the coefficient for concrete structure is 1.8, the dimension of spillway are calculated as using equation 1313. So once we identify Q from equation 2.21, we can compute L based on 13.13. C is 1.8. Yes, if C or concrete structure is 1.8, this is based on the description 13.13. L, so we need to find L. Yeah, L. H is the depth of flow should be between 0.5 and 1.5. This is based on the previous slide. The depth of the spillway between 0.5 to 1.5 meters. So we assume 0.75 meter. Then we can calculate L is equal to 4.5 meters. The spillway length. 4 meters tengah. The box in the spillway should have a total 4.5 meter with two sides of 1 meter. One total radius distance of 1.5 meter. Exercise. Determine the cut and fill volume of soil for a 150 meter terrace with balanced cross-section on a 5% slope. If the channel depth is 0.4 meter, the freeboard is 0.06 meter. This is based on sample. Sample 13.3. Yes. So 13.3, first calculate the terrace height, which is h. So h equal to d plus freeboard. In this case, the depth is 0.4. 0.4 plus freeboard is 0.06, so 0.46. The required depth of cut and fill, that one refer to equation 13.2. So h is in this case 0.46. The terrace height you calculate already. Plus s is the slope, which is 5%. So to use here, you need to divide by 100% times W. W is the width of the terrace. In this case, the terrace width is width. So without the width, we cannot calculate W. We cannot calculate C and F. Yeah. So in this case, yes, we still need to calculate, but in terms of W, the final answer is in terms of W. Yeah. So in this case, the answer is W. No, jump it. So need to leave the value in terms of W in this case. So 0.46 plus 0.05 W divided by 2. Unless the question asks to find the look W. If you want to find the W, can you need to use a equation, the derivation. There are two F and two C there. Or refer to page 314. So 2F equal to H plus SW or 2C equal to H plus SW. So either one need to choose. So need at least two equations. To determine this one. Okay. Next one is the soil loss for sloping in Ohio in 13 megagram or 13 ton per hectare. Determine the slope length. The spacing needed to reduce the loss of soil from this being by 10%. If the USL effector value are K or already given everything, so determine the slope length into the spacing. So refer back to A. So A equal to question 0.5. R is given. No, R is not given. A is given 13 megagram. Okay. R is not given. K, but we can find R. This is Ohio. R K 0.15 and it's not. So L is 140. S is 7%. C is 0.25. P is 0.4. Line interest spacing. This is based on example 13.32 and number 2. Yes, 15 Question 1 is based on 13.3. So based on 13.2, so tak sini Ohio kan? X is a geographical location. S is the soil slope. Y is the soil condition. Vi is the difference in height between two adjacent or succeeding terraces, which is the uh, terrace spacing. Hi is the horizontal distance between the traces, which is the slope length. Hmm. Takun value aja. Cari soalan data. So both question based on 13.3 and 13.3. For example, slope length. Slope length is based on the horizontal distance. So horizontal distance. Tinggi. That one is using equation 13.1 x times s plus y 100 over s. So x is Ohio. Nah, just check Ohio's too. But value is based on 13.13. Figure 13.13. The monogram. That's in Ohio. S is given in the equation 7% plus y is the soil erodibility. Soil erodibility. Okay. Soil erodibility. So that one is based on value of of value of LS, topographic factor. So this is okay. Ya, sih lengkap soalan. With LS got several value in this case. From LS, you can determine value of Y, then you can calculate the HI. VI is same using the same value. This is the last slide. Okay. Any questions? Your attendance first.
Doctor, can I know what should we focus for the final exam? For example, like, do we have to focus more on soil pollution or maybe uh, noise pollution?
Uh, Actually, Dr. Ibrahim is the course coordinator. I was tasked to provide the project only. So meaning if there are two questions, should be two questions. One from Dr. Ibrahim, another one from Abizal, Mr. Abizal.
Alright, alright. Okay, thank you, Doctor.
Thank you, attendance. And don't forget to submit the project. If you require extension, you email me. Thank you. See, you can next semester, I think. Semester we teach advanced optimization with Dr. Farid, Dr. Asron. That one, yes, I am preparing one question for final exam.